This week, running the seminar and being a speaker, I get the pleasure of introducing myself. So anyway, I think most of you know who I am. My name is Middleton. I'm a professor at CMU. And the talk I'm going to give today is entitled Circular Orbits on a Warped Spandex Fabric. This talk was based on originally Michael Langston, our graduate from last year, did his senior research project on exactly this topic. And I kind of took off where he left off at last year, and I spent the summer then kind of learning from some of the mistakes that we had made together as far as some experimental stuff and that kind of thing. This paper you can't see down below, but it has been accepted for publication in American Journal of Physics. I don't know when it's going to happen, but it's at the editorial process right now. All right, so let's go ahead and get started. So I have to start every talk off somehow connecting this to general relativity, right? So anyway, let me give a little discussion of general relativity before we get started about talking about a spandex fabric. So Einstein's theory of general relativity describes gravity as the warping of space and time due to the curvature or due to the presence of matter and energy. And this equation on the top is called the Einstein field equations. It's actually in general a set of coupled, well there's 10 in general, coupled nonlinear partial differential equations in general. You don't need to know the structure, but what you should realize there's on the left-hand side that g mu nu, that is called the Einstein tensor. It describes the curvature of space-time. On the right-hand side, there's some constants, and then that's multiplying T mu nu. T mu nu is the stress energy tensor, and that's effectively telling you about the matter and energy that you have in your space-time itself. So effectively, John Wheeler once eloquently said, summarized general relativity effectively as this: matter tells space how to curve, and space tells matter how to move. And that's basically the essence in general relativity. In general relativity, gravity is not thought of as a force, but rather the manifestation of the warping of space and time. This is a picture that comes off of a typical, graduate level text on general relativity. And what people typically do is they think then in terms of, to think about this curvature of space-time, you often envision a spandex fabric or some type of fabric pulled taut and place a mass on top. That mass causes that space to warp, and then the analogy is often drawn to then thinking about particle orbits as or orbits of planets is due to the fact that these planets are in fact moving in a warped space-time. And this is kind of effectively the analogy that's often used in general relativity. So basically the essence of this talk is to kind of probe this conceptual analogy. We're basically working out the physics behind the analogy that's often used. So in a typical undergraduate general relativity course, one of the first things you study is what's called the Schwarzschild solution. This is an exact solution to the Einstein field equations. And what this does, it describes the geometry outside of a spherically symmetric, non-rotating massive object. So effectively a ball or a star that's not rotating. And again, the exact solution is easy to write down, so we can write down the geometry outside of that space-time. And again, that's the whole game of general relativity, is to understand the geometry outside of your mass or outside of your object, here being a spherically symmetric mass. Now, what you have to kind of do effectively, or what it's nice to do to wrap your brain around it, you're trying to envision then this four-dimensional warped space-time, and that's quite hard to do, right? So what you do then in general relativity often as an exercise is you construct what's called an embedding diagram. And what an embedding diagram effectively is you take your four-dimensional geometry, your four-dimensional space-time, you look at one moment in time. So you effectively think of a photograph of this guy. And then you look at, in spherical polar coordinates, if you look at your polar angle theta, you look at theta equals pi over 2. And what that does is effectively reduces your four-dimensional space-time to a two-dimensional, effectively, surface. And then what you do is you construct what's called an embedding diagram. An embedding diagram is you take this surface that exists in a two-dimensional surface in a three-dimensional sense, and you force then the geometry of that two-dimensional surface to be equal to the two-dimensional spatial curvature of that slice. And you think of then you can wrap your brain around this concept in general relativity, this warped space and time. Now, for the Schwarzschild solution, it's actually very easy to do. You take this two-dimensional surface in a three-dimensional space, and in this, of course, this two-dimensional surface has cylindrical symmetry. So those cylindrical coordinates would correspond to z, r, and phi, if you will. And there's symmetry in the phi direction. And then z is a function of r, which describes then this two-dimensional surface is given by this equation. I am working in units where c and g are set equal to 1 here. So this is just the square root of this r minus 2m effectively. And what this is this two-dimensional surface that has z as a function of r described by this guy has the exact same curvature as then this two-dimensional spatial slice of the full Schwarzschild solution. What then is often done is one takes a logical leap, or what often is done is by this embedding diagram, people then start to think and use this analogy to then envision then some object rolling on this two-dimensional surface as the analogy itself. You should realize that these are actually different things. This embedding diagram, that is an exact solution that describes the geometry of this Schwarzschild solution in 2 dimensions. But then the question is there any warped two-dimensional surface that will, if I get a marble, say, rolling on this surface, can I get then the exact same motion that one would in fact get for, well, a planet orbiting around the sun? So that's what we want to, answer here in the next couple of slides. All right, so let me then jump from Einstein's theory of general relativity to Kepler's third law. The reason why we're going to talk about Kepler's third law is at the end of the day, this is the expression we're going to want to come up with, this Kepler-like expression. So for simplicity, this is the simplest way to do this. If I look at some massive object, say capital M, maybe that's the sun or something like that, and I have some other mass that's orbiting, maybe it's a planet or something like that with small m, and it's moving in a perfect circle. This is the easiest way to do this. I can then say, what is the net force acting on this little mass? And of course, it's given by, in Newtonian theory, Newton's universal law of gravitation, gmm over r squared. That's the net force acting on my object. I set that equal to mass times acceleration in centripetal coordinates. That's mv squared over r. And then what I can do is I can connect the speed of this planet orbiting around the sun to, well, the speed is a constant, so it's the distance traveled, which is the circumference 2 pi r, divided by the period. Capital T corresponds to the period of time it takes this planet to orbit around the sun. If I take this expression for V, substitute it into Newton's second law up above and rearrange, this is what I find. And this is called Kepler's third law. This was discovered by Johannes Kepler by looking at Tycho Brahe's data before Newtonian theory was understood. We're going to come up with a Kepler-like expression for our treatment here today as well. So what I want you to realize, this is just a constant, so who cares about this? This is the period squared, the time it takes this planet to orbit around. This is the radius of the orbit, and m is the central mass. So this gives me a relationship, Kepler's third law, this gives me a relationship connecting the time it takes the planet to orbit around the sun to the radius of the orbit itself and to the central mass. And this is how astronomers are able to, in fact, determine then the mass of that central object, right? It's because they can measure then the period it takes some planet to orbit around our sun, for example. You know the radius, you can calculate the mass of the planet versus using some big scale. You should also realize that Kepler's third law has nothing to do with the mass of the planet that's doing the orbiting and stuff. It doesn't matter how massive this guy is. Kepler's third law holds for whatever this guy is. I'm bringing Kepler's third law up because we are going to find out an expression similar to this guy for our spandex fabric. Let me give you a basic outline of the paper and the talk today as well. There's basically 5 parts. The first 2 parts, I'm not going to lie, it's a little bit heavy at the beginning. It'll lighten up later on. These first two parts are the theoretical aspect of this whole thing. These second 2 parts then represent the the experimentation itself and our Kepler-like expressions. And then at the very end, I'm going to come back to general relativity and compare to circular orbits and general relativity effectively. So the first thing we're going to do is we're going to consider a marble rolling on a cylindrically symmetric surface. I'm not going to specify in this first part what that surface is, just some surface that has cylindrical symmetry. We're going to come up with the equations of motion describing this marble rolling on this surface, and we're going to use Lagrangian dynamics in order to do that. The second part, and this is the hairiest of the lot, which Michael can attest to, this is the shape of the spandex fabric. So what we're going to do is we're going to actually determine, well, an equation which determines the shape of this spandex fabric by using the calculus of variations. From there, then I can then connect these two effectively and come up with a Kepler-like expression. But I can't get an exact expression. But what I can do is I can find a Kepler-like expression in the small curvature regime. What does that correspond to? The small curvature regime corresponds to where the warping of that fabric is small, so where the slope of the fabric is small. And then we're going to also come up with a Kepler-like expression in the large curvature regime. The large curvature regime is if I have a huge central mass in the center, the walls of that fabric is going to have quite a large slope. So when that slope is in fact very large, I can also come up with a Kepler-like expression in that regime as well. All right, so first off, let's talk about a marble rolling on a cylindrically symmetric surface to begin with. This is, of course, the Lagrangian that describes a marble of mass m moving on this cylindrically symmetric surface. There's effectively 3 terms. This is just v squared. So this is the translational kinetic energy of the marble. This is the rotational kinetic energy of the marble. The marble's rolling on the surface. Minus the potential energy. This is just gravitational potential energy of the marble itself. Now, a couple things to notice. First off, I'm talking about a marble which is a uniform marble. For a uniform spherically symmetric object, the moment of inertia is 2/5 mr squared, which you know, m being the mass of the marble and r being the radius of the marble. And what we do in this work is we assume that the marble does not slip. And if the marble doesn't slip, then the angular speed is related to the translational speed of the center of mass. Now, if I multiply these two terms together and multiply by 1/2, what I find is 1/2 I omega squared is 1/5 mv squared. That allows me to effectively combine these two terms, and I merely change that 1/2 to a 7/2. Okay? So that's the first bit. The second bit to realize, if you've had advanced dynamics, again, we talk about Lagrangian dynamics a lot in that class, it appears that there's three coordinates here, three generalized coordinates, r, phi, and z in cylindrical coordinates. However, this marble is going to be constrained to reside on the surface itself, which means that we have an equation of constraint. Effectively, you tell me what r is, and I'll tell you what the height of that fabric is itself. So what I can then do is, in this first part, just generically say that z is some function of r, and I can then put this into the Lagrangian and express then the Lagrangian in terms of r and phi. So I do, in fact, have two generalized coordinates. All right? Now, if I have two generalized coordinates, that means I'm going to have two Lagrangian equations of motion. One Lagrange equation of motion corresponds to, it effectively just tells me that I have conservation of angular momentum. The second one then is the Lagrange equation of motion for the radial coordinate, and this is the one that we're interested in here. If I take the Lagrangian from the previous slide and I recognize the fact that z is a function of r and stick it into the equation, this is the equation of motion that emerges. I should have mentioned on the previous slide, which I forgot to, the dots correspond to time derivatives and the slashes correspond to r derivatives. So all we did was we effectively used the chain rule to say that z dot was dz dr dr dt, or z slash r dot. So this is in fact the equation of a motion for a marble rolling on a cylindrically symmetric surface without specifying anything about that surface whatsoever. Now, what I can do, I'm going to answer now the question that I addressed on the slide number 2. I'm going to compare it to the equation of motion for planetary orbits. This is a Newtonian theory. If I look at GR, I get an additional term. It doesn't matter. The point is the same either way. If I compare these two equations, I can say, is there some surface, z is a function of r, which will allow me to then get exactly planetary-like motion? And the answer is no. There is none. If you compare closely, look at, if I chose z to be proportional to 1 over r, a 1 over r type of a curve, proportional to, I can get this term and this term to match up. This term and this term matches up. This term and this, I have an r double dot term here and here, but notice I have an additional r dot squared term. There's nothing I can do to make these two the same. So the takeaway is this, and this was, you can't see any of this thing's too low. I can go down a little bit with this thing. Nope, that's as low as it goes. So all of my references down below. There was a paper published in American Journal of Physics last year, 2012, by English and Moreno that actually showed this result, that there is no cylindrically symmetric surface which will allow me then to get exactly the planetary motions that I see in Newton's second law. All right, now I gotta be a little careful. When r dot is equal to 0, however, there is, right? But that's not very interesting because most orbits are not circular, they're elliptical. All right, so let me go back to that equation of motion. This is my generic equation of motion, and what we're interested in, we try to simplify the procedure by, we were looking at circular orbits. For circular orbits, r dot is 0, and r double dot is 0, which means that this term and this term go away. When this term and this term go away, this expression reduces to this very simple equation of this form. Where notice I use the relation phi dots, or r phi dot is 2 pi r over the period t. Here I have an expression involving r, the radius of my orbit, t, the period, the time it takes this marble to orbit around the central mass. And what you can find, what you see from this expression is that this is proportional to z prime. Z prime is the slope of the surface. So if you tell me the slope of the surface, I'll tell you a Kepler-like expression. That's effectively the takeaway from this slide. This expression is linearly dependent on the slope of the spandex fabric. So all I need to know is z prime, and I can tell you what the Kepler-like expressions are. This brings us to part 2 of the talk. This is the shape of the spandex fabric itself. In order to find the shape of the spandex fabric, the way in which we went about doing this is we consider the total potential energy of the central mass spandex surface. we construct the total potential energy as an integral. We're going to use the calculus of variations. So I need to write the total potential energy, I'll call PE, as an integral functional. Those of you who had me in advanced dynamics are probably remembering the language and try to keep it the same. We're going to construct a total integral describing the total potential energy of my spandex fabric central mass surface. And we have three contributions. Number one, as I put a mass on this spandex surface, there's going to be elastic potential energy in that spandex surface itself. So there's a contribution to the elastic potential energy of the spandex surface. Number three, I'm going to slap or put a large central mass on the center. There's a gravitational potential energy of that large central mass as well. Now, if you saw Michael Langston's talk last year, this number two is a new addition to that. So this summer I realized that this term is actually quite important. The spandex fabric itself has mass, and since the spandex fabric itself has mass, it has potential energy. So in this work, I generalized this summer that I did last year, or that I should say that Michael did, to include the gravitational potential energy of the spandex, and this actually is quite an interesting contribution. I should note that number 1 and 3 were considered back in 2000, you can't see it, but back in 2002 as a separate AJP paper that arrived at Gary White's relation, we'll talk about this later, by considering exactly the same thing. So what we do, this is a technique, what we're going to do in the next several slides, we're going to be on going through the details of this effectively. We construct the total potential energy from these three terms, and then I'm going to have an integral functional. I can take that functional and then, well, I want to apply it or use the calculus of variations. The calculus of variations effectively will say, I'll take this functional, stick it into the Euler-Lagrange equation. That will give me an extremum solution, which corresponds to either the maximum or minimum, and in this case it corresponds to the minimum total potential energy. And it turns out that this spandex fabric will in fact choose a shape that minimizes the total potential energy of this total system. All right, so on the next 3 slides I'm going to go through number 1, 2, and 3, not in too much detail, but to kind of give you the gist of this thing. The first thing we're going to consider is the elastic potential energy of the spandex fabric. Imagine, and I forgot to even talk about on the first slide, that spandex fabric was a 4-foot diameter trampoline where we draped a spandex surface over this guy, or a spandex fabric over this guy. It's effectively a circular surface with some radius capital R, right? So what I'm going to do is I'm going to consider a concentric ring of very thin thickness, a differential thickness. So I can write down E stands for elastic potential energy. This is an infinitesimal contribution to the total, or to the elastic potential energy of this differential concentric ring. And all this effectively is 1/2 k times the stretch squared, which each and every one of you know from intro physics, right? K is the spring constant of this differential concentric ring. What about this guy here? Well, push the wrong button. What about this guy here? Let me look at a little bitty, again, we're looking at a concentric ring. The width of that guy has a width of dr. If I stretch that fabric, this guy will then be stretched to this amount here, where dr, this was the original length. Again, the fabric is constrained to its radius. So this is my old dr, and now I have a stretch in the z direction, so this length becomes the square root by Pythagorean theorem, the square root of dr squared plus dz squared. The difference between this term and this term corresponds to the stretch. The stretch squared times 1/2 k, that is in fact the total potential energy of this, well, differential concentric ring. Now, what we need to do then is connect this spring constant K to what's called the modulus of elasticity. The spring constant K, in regards to the modulus of elasticity, kind of a nice way to think about it, I was thinking about the last couple of days, is kind of like the resistance of a wire to the resistivity of a wire, right? The resistivity of a wire is a property of the wire itself. The resistance of a wire depends not only on the resistivity, but also on the geometry, the length and the cross-sectional area, and things like that. The same thing goes for the spring constant. A spring constant is constant for a given spring, but if I take a spring and I cut it in half, I actually change the spring constant itself, right? If I take, say, for a given radius out, if I look at half of the dr that I had from before, my spring constant is going to double. So for a given r, k times dr is a constant. And then also, if I look at, well, what if I look at different radii? If I look at twice the radius, the spring constant also changes as well. How so? Well, the way to think about this effectively is if I think of this concentric ring, I can think of a series of little bitty springs wrapped around. If I double my radius, I double my circumference. And if I double my circumference, I double the number of little springs that I effectively have for a given circle, which means what? If I have twice the number of springs that are in parallel with one each other, I am going to have double the spring constant K. So for a truly elastic fabric, this E, the modulus of elasticity, is a constant, and it's related to the spring constant K by this form here. So what do? I solve this expression for K, I plug it into this expression here, I pull out a dr, and then what I want to do is I want the total elastic potential energy of the fabric, which requires me to integrate over the radius of the fabric. So if I integrate this expression from 0 to r over the radius of the fabric itself, this is the total elastic potential energy of the spandex fabric itself. All right? Now we got to talk about gravitational potential energy. This is the new contribution that came in this summer. This spandex fabric has a mass, and therefore it has a potential energy as well. If I again think of the same differential concentric ring, I can talk G is for gravitational, S is for the spandex. I can take an infinitesimal contribution to the potential energy of this concentric ring is what? Well, this is just mg times my height, right? Where my mass here is a differential mass. It's the mass of that ring, and Z is the height of this guy itself. Now, what I can do is connect the mass to the unstretched areal mass density. So this sigma sub 0, you'll see this later on in the talk. Sigma sub 0 is the unstretched areal mass density. Mass per area, 2 pi r, that's the circumference times dr. That's the area of this concentric ring. So the product of these two is in fact the mass. Now it took me a little while to think about this and to reference some sources and things like that. I started thinking in terms of, well, if I put something on top that's going to stretch the fabric, that's going to change the mass density will become a variable mass density. But that doesn't matter because the mass of this differential segment is going to remain the same. So what I can then do is use this first equality, plug this expression into this guy here. That tells me the gravitational potential energy of that ring. If I then integrate over the ring, that tells me the total gravitational potential energy of the spandex fabric, written in terms of an integral. I need to write all of these terms, guys, in terms of an integral. Here it is, 2 pi sigma sub 0, this is just some constant, G is 9.8 meters per second squared, times RZ dr, and I'm going to integrate over that guy. That's 2 of the 3. Last one's very simple. How about the gravitational potential energy of the center, the central mass? We put some big massive ball in the center of this guy. What's the potential energy? It's mg times the height. So it's Z is a function of r. Here I'm looking at the center of the fabric, so r equals 0 here. Capital M corresponds to the mass, capital M is the mass of the central object. Times mg times Z, that's the gravitational potential energy of the central mass. This is a trick, and we pulled this right out of that previous paper I talked from before. What you can do is write this in terms of an integral. How so? Well, Z prime is dz dr. dz dr times dr is just dz. If I integrate this from 0 to r, at r it's 0. So then I need the minus sign because when I evaluate the second limit, that gives me this term here. Okay? So there it is. Those are the 3 terms in a nutshell. This is an approximation. Notice we approximate the central mass as being point-like. In all reality, this guy has a finite size to it, right? Anyway, let's put it all together. I put it all together, and this gives me the total potential energy of the central mass spandex system. There's 3 terms: the elastic potential energy, the gravitational potential energy of the spandex surface, and the gravitational potential energy of the total mass, which I write as a total integral, where this F is called a functional. It's a function of Z, the height, the slope, and R itself. Here's the functional. Here's my 3 terms. This first term here is that E recognizes the modulus of elasticity. This guy involves R and Z prime. This term is the integrand that's to be integrated to give me the elastic potential energy. The second term, bunch of constants out front, sigma 0 being the constant areal mass density, which we can measure, R times Z here. And then lastly, this term is just mg times Z prime. This guy depends only on Z prime. This is the term due to the central mass. So what do? I got my functional. I want to extremize this guy. What I want is the extremum or the minimum of the total potential energy, because the total of the potential energy is going to tell me then the shape of the spandex fabric. Very simple. If you take calculus of variations, you know this. You take this functional. This is called the Euler-Lagrange or the Euler equation. You stick it in, take these derivatives, and you generate yourself a differential equation. And here it is. Last semester when Michael considered this guy, or last year I should say, when Michael considered this guy, he got exactly this without this term on the right-hand side. Luckily, by including this gravitational potential energy spandex surface, I can still integrate it the same way Michael did. So this guy is a derivative with respect to r of this whole thing is equal to this right-hand side, which is just a function of r. I can multiply by dr and integrate. When I do so, I set the constant of integration equal to 0, and this is the equation that I arrive at. The left-hand side, notice it just depends on r and z prime. Z prime is the slope. It's a nasty differential equation. It's nonlinear. It's ordinary. That's the nice thing. But it's nonlinear. If you square this thing out, it's like fourth order, I believe. It's disgusting. You tell me the inputs, effectively, the masses I start off with, and I'll tell you what z prime is if I could solve it exactly. Let's explore the right-hand side. M is the mass of the central mass. What about this guy? Well, this guy, sigma 0, that's the mass per area times pi r squared. That's the area of a circle. So what I see then is this is how the spandex fabric itself contributes as far as the mass does. The shape of the spandex fabric is determined not just by the mass of the central mass, but also the mass of the spandex fabric interior to the orbit of the marble itself. These two terms effectively are competing for dominance. Now, what is this alpha? Alpha, we're just going to call it a parameter. It's effectively proportional to 1 over the modulus of elasticity. Bigger modulus of elasticity, smaller alpha. All right, so let me recap. If you missed the last 5 slides or you're not paying attention or whatever, let me just recap. Here's where we stand, right? This is where we need to get. I have 2 equations. This equation is my circular equation of motion. You tell me z prime, I'll tell you Kepler's law. The second equation, this guy determines z prime. Effectively solve this guy for z prime, stick it into here, and then you have a Kepler-like expression. Again, I cannot solve this guy exactly, but what I can do is I can explore the small curvature regime and the large curvature regime. Again, z prime is just the slope. If I look in the small slope regime, I can perform everybody's favorite Taylor series expansion and keep the first 2 terms. If you look closely, if I stick this guy into here, I'm going to have 1 minus that 1, that goes away. I get a z prime squared times a z prime, that's z prime cubed. I can solve for z prime then, stick it into here, and it gives me a Kepler-like expression. Yeah?
I guess you have a different Kepler's law for different radii, but you can only cope with large and small radii.
Different Kepler's law for different radii. That's right. So, well, in essence, there would be one general expression if I could solve this analytically, but I can't, right? So what I'm going to do is find an approximate solution in each regime, a Kepler-like expression we're going to talk about, and you'll see that soon. That's where we're going. So I perform a Taylor series expansion. I can solve this guy for z prime. I can then analyze this guy in a small curvature regime. We'll do that first. I can also look at the large curvature regime. If I have a huge central mass, the walls of this guy is sloped nice and large. So what I can do then is I can perform another Taylor series expansion. Z prime is big. If I pull it out of the square root, then I have a 1 plus 1 over something huge. I can then expand that in a Taylor series expansion like so. If I put this into here, I'm going to have 1 over z prime. I'm going to keep only that first term. When I multiply it by z prime, I'm going to have a z prime minus 1. I can again solve for z prime, stick it into here, and get another Kepler-like expression. All right, so now at this point, effectively the theory is over with. Let's now talk about the experimentation. I'm proud to say this is the first time I've ever given a talk with data that I've actually taken myself. Experimental physics is pretty cool, yeah. Anyway, I learned a lot from doing this stuff. But anyway, and I should say Michael and I, we did all this stuff together last year. So anyway, I do this, I do exactly like I had said. I'm looking in the small curvature regime. I do the Taylor series expansion, I plug it in, and here I obtain an expression. What do you see? This is a big ugly constant. We're going to actually determine this experimentally in a moment. On the left-hand side, I have my period cubed. Over here, I have my radius. I can measure the radius. I can measure the period. I can measure the areal mass density. I can measure R. I can measure my central mass. I can plot this guy. And that's what we're going to do. We're going to plot this versus this, and I should find a straight line. Now, first off, let me show a couple things. What I can do, I effectively have 2 competing terms tied up under this square root in the denominator. If I look when the central mass is much, much bigger than the mass of the spandex fabric interior to the marble, if I neglect this term altogether, my Kepler-like expression reduces to this guy here. This was first found by Gary White and Michael Walker back in 2002. They actually did the same analysis, but they looked at Newton's second law instead of considered energy concepts, and they first arrived at this and did some experimentation as well. If you remember Kepler's third law, effectively the powers are switched. Kepler's third law for planetary motion says that t squared is proportional to r cubed. For a spandex fabric, or for a marble on a spandex fabric in a large curvature regime, it's the opposite. It's t cubed is proportional to r squared. And also the mass difference 1 over square root of m versus m. The other regime, though, what about if my central mass is small? If my central mass is small, then this term is going to dominate. If this term is going to dominate, I'm having r squared to the 1/2 power, that's r squared over r is r. So I find a different Kepler-like, even in this regime here, I find 2 different effectively asymptotic behaviors depending on the masses. Here t cubed is proportional to R. So then you can ask the question, when are these guys on equal footing? And you simply plug the numbers in. We measured this last year. The sigma 0, I believe, was 0.19 kilograms per square meter, if I remember correctly. We're in the large radii regime. These radii came out to, I averaged over these guys, is about 0.4 meters. You plug these numbers in, you find the mass is about 100 grams. So when my central mass is about 100 grams, it's on equal footing to the mass of spandex fabric. So what we did then, or what I did this summer, was I explored around this regime here to see, can I in fact get experimental agreement with my theoretical analyses? Let me talk about the experiment. And again, a lot of you have seen this already before. This is my spandex fabric. This is one of those old school 1980s style trampoline fabric, or trampolines, 4-foot diameter exactly. What we did was we stripped off the actual trampoline itself. And this is how I changed things compared to what Michael did last year. By mistake, Michael and I, and Dirk, I believe, is actually a part of it as well, we nonchalantly tucked this fabric in without being very careful. And what we did by mistake was effectively give rise to an initial stretch. That initial stretch complicates the physics, as Michael can attest to. It makes the physics very complicated, and we tried to work around it anyway. So what I want to do is repeat the process this summer, guaranteeing that I have no pre-stretch. The way I did this was I just took a big piece of styrofoam and I cut it out such that it fit perfectly inside of here. And I effectively made a tabletop. Once I made the tabletop, then I draped the spandex fabric over the top, and we took a truck tie down, wrapped it around the outside, ratcheted that guy down nice and tight so it wouldn't move, and then I removed the styrofoam insert from inside. I was surprised to see just how much this guy actually warped. No central mass at all, and this spandex fabric dropped about 4 inches for 48 inches. Quite a bit. So then I started thinking, well, could I even get, in fact, an orbit with no central mass? And the answer is yes, I actually got one. So then if that's the case, then, and this was before I included the gravitational potential energy of spandex fabric, then I wouldn't get the right dynamics. I realized then that spandex fabric, the contribution to the gravitational potential energy of the spandex fabric itself was important, and that was a new contribution I put in this summer. Anyway, I have zero pre-stretching whatsoever. Here's the fabric. We mounted, you're seeing a picture taken from when the camera is mounted directly above this guy looking down onto our 4-foot diameter frame. As you can see on the outside, here's a little ramp. We took a ramp and we mounted it to the outside perimeter. What this allowed us to do effectively was to control our initial conditions. We could control our initial radii and we could control our initial speed so we can get nice circular-like orbits. We then took these video clips. I ran this about 12 times or so. Once I would run it about 12 times or so, I then looked over and I found the one that looked the most circular. And then I would import that into Tracker and analyze that particular orbit on Tracker. What Tracker will allow you to do is take your video clip and time step it forward by 1/30th of a second. If you look up here, I see about 60 diamonds. That tells you it took this marble about 2 seconds to make a full revolution, right? Now, Tracker's really nice. You can actually scale this guy by measuring the size of the diameter. I can scale it. I can determine the XY coordinates of each of these diamonds and therefore know the radius. It also gives me a timestamp so I can calculate the period. So we know what? We know the radius, we know the period, and we also measure the central mass. This mass in the middle corresponds to, I believe this was the 0.6 kilogram mass here in the center. So we did exactly this. We calculated the average radius for each and every one of the radius for each and every one of these guys. And then I played around with the data for a while, and I realized the best way to do this, to get the neatest data, was to actually let this guy run a full revolution like so. As you can see, it got back to where it started. It's off a little bit because there's some losses and things like that. We calculated the average radius. We averaged over all of these guys. We measured the time it took to make a full revolution, and we could plot these guys. What you're seeing on the screen corresponds to one data point. And then what we do is we shifted forward by 1/8 of a revolution. When Michael was doing this last time, we were taking 4 data points. We went around. I looked at every single data point for more accuracy. The next data point would be generated by then looking at my initial data point as being here, going a full revolution around, and that'd be data point number 2. Then we shifted up another 1/8 of an inch or 1/8 of a revolution and do it again and generate all these data points. And then we change the central masses out as well, and we could then plot on Excel how these things vary. This brings me to some data. This is the data that we took effectively. So what we do, this is a plot of t cubed versus this quantity over here. This guy was being multiplied by an overall constant. Now, what's pretty surprising to me is a couple things. First of all, I was shocked at how good the data actually came out when we were careful. It actually came out really good. The R squared value of the line of best fit is 0.994 for this guy. Pretty good. And again, I can tell Excel to lay down a straight line and tell me the slope of the line. And the slope is given by this term here, 45.6 kilograms to the 1/2 second cubed divided by meters squared. What does this tell me? Well, if I go back to my original Kepler-like expression, the slope is this guy here. I know everything. I know G, I could solve for alpha. And if I know alpha, then I know the modulus of elasticity. This is a way to measure indirectly the modulus of elasticity and this parameter alpha in this small curvature regime. And these are the numbers that we get. If you look at the time scale here, I'm looking at, this is t cubed, so it's about 6 to 26. That corresponds to 2 to 3 seconds. That was about how much time it took this marble to go around in this small curvature regime. What's pretty impressive, I thought, I was quite happy when I got this, these data points up here correspond to 0 central mass. No central mass at all. I could actually get the marble to, what would happen? The marble would go around about 1.5 times, and then it would damp down immediately and roll right in towards the center. That still allowed me to find 3 data points because I would shift by 1/8. These 3 data points remarkably fit just perfect. 0 central mass. Our old analysis would never have accounted for this guy because my denominator would have exploded. Anyway, that takes us to part 4, which was the large curvature regime. I do this, sorry, yeah, go ahead.
Yeah, so can you measure the elasticity constant independently somehow?
Yes, I'm going there, yeah.
Okay.
Yeah, you'll like the next slide. So, yeah, it took me a little while to figure out how. I'm going there. All right, and yeah, I'm going to build up to why we had to do this. So what I had to do then was, we looked in the large curvature regime when z prime was big. I do the same game I did before. I take my shape equation, I expand for large z prime. I then stick it into the circular equation of motion, and out comes a completely different Kepler-like expression in this regime. In the large curvature regime, this corresponds to when my Spandex fabric is warped a lot, and I'm looking deep inside the well itself. In that regime, the period is proportional to, well, the radius divided by this guy here. As you can see, again, there's 2 competing terms of the denominator. One is the simple radius. M is the mass of the central object, and this alpha is 1 over the modulus of elasticity. Now, since it's tied up under the square root, effectively what we had to do is I could plot t versus this guy here, but that requires me to put alpha in. And then I would expect to get a straight line where the slope corresponds to this guy here. First of all, let me mention a couple things. If I look when r is small compared to this guy here, so I'm really far inside the well, then what I find is t is proportional to r. This corresponds to the solution to the 2-dimensional Laplace equation in cylindrical coordinates. This was mentioned again in some of these earlier papers as well. Now you may think I could do the other thing. I could look in this large r regime inside the large r compared to m alpha, but I can't look in that regime. Let me kind of explain why. If I look when r is much, much greater than m alpha, my shape equation reduces to z prime is proportional to 1. But this expansion was performed only when z prime was big. That tells me that I cannot ignore this regime, or another way to say it is that this Kepler-like expression is not valid in this regime. So what I did was, again, we measured r, we measured t, we measured the mass. We had our alpha from an indirect measurement in the small curvature regime. I plugged this into Excel, and I get poor results. Poor results means non-linear. It looked terrible, and I couldn't figure out why. But what I was able to do is I started playing around with Excel. Alpha was just an input. So I started playing on the numbers. And I realized if I made alpha smaller, I could make it linear. So then I started thinking maybe the modulus of elasticity is not really a constant. Maybe it's actually changing. And if it's changing, then maybe I can account for this. This brings me to, then how do I measure the modulus of elasticity? Here's how you do it. This corresponds to a photograph. I've now taken that camera that was mounted up above and took it across the lab and taken a close-up zoom in. Here's the Spandex fabric itself. This corresponds to 7.7 kilograms. That's what, about 17 pounds, something like that, 15 pounds? Quite a bit of mass underneath this guy, right? And you can see this thing's causing it to warp a lot. But what do? I need to find alpha. I need to experimentally determine it directly. If I go back to my shape equation, in the large curvature regime, z prime takes this form, and I keep the first 2 terms. I can easily integrate this expression, and that tells me how it's normally interpreted is the shape function. Z is a function of r. That describes the curve of this guy here for a given mass. But then I started realizing I could think about it differently. Instead of thinking of it as a shape equation, z is a function of r, and for a given mass, I could do the opposite. I can hold r constant and change the mass. So then if I think of z as a function of the mass, what do I find? This is what my expression becomes. This is thinking of the height as a function of the mass. What is r sub b? This, what we're looking at effectively, I had a central mass inside this guy, and we used an adjustable pipe clamp to tighten it down the outside. We then fashioned a little basket to hang underneath this guy, and we could load weight masses on top of that guy. So this r sub b corresponds to this radius here. It's effectively the radius of this ring itself. So this, the left-hand side, is effectively the scaled mass, and m is just the mass that I hang. So, and alpha, of course, is the parameter that I'm after. So I realized that if I could actually measure then the height of this guy for given masses, we could plot this and find alpha. And if my spandex fabric is truly an elastic fabric, then I should expect when I plot this versus this, the slope of that line is going to be alpha. And if this is really an elastic fabric, then alpha should be a constant, right? Now, if you look here, I have a bunch of different diamonds. There's 24 total. These top 10, I started off at just the basket mass itself, and the central mass was 0.274 kilograms. I stepped it up by 0.1 kilograms up to 1.174. That brought me to here. And then I started to jump up by half a kilogram intervals. So I went from 1.274 up to 7.774. And here you're looking at that 7.774 kilograms. This was me underneath it. I was actually getting a little nervous that this thing was going to snap. And I was going to...
So each of the diamonds then is a different mass?
Each of the diamonds corresponds to a different mass loaded on that guy. That's right. So and again, you could do the same thing. I was able to measure the height of these blocks, put it into tracker, measure z, measure r, measure m, determine alpha experimentally. So let me show the data. And you can kind of see what's happening. Look at the gap is getting smaller as I go down. It turns out that alpha is not a constant. The modulus of elasticity is not a constant for spandex fabric, as I assumed, or we assumed at the beginning. Yeah?
Aren't you assuming the same alpha across the entire...
Yeah, that's a great question. Yes.
Where some parts might be, I think it was a bungee cord, elastic, and then when the fabric around the outside comes to a home.
Yeah, so that's exactly what we're doing. We're assuming effectively that the value of the alpha is the same throughout. It's a universal property of the spandex fabric itself. And you'll see we get pretty good results when we do that. So now this is a plot, just like I said from before, this scaled height z versus this mass. I just take the mass and subtract off the initial mass. And here's my data points. Now I got 3 different color combinations here. This region down here, these black diamonds, these correspond to the small mass regime. This mass regime was effectively the mass we were probing in the small curvature regime. This intermediate region we didn't explore at all. And then the large curvature regime, when I was deep inside the well and we actually loaded this guy down, this was the range of masses that we looked at here. Now, although this is absolutely not a constant, if I look in this regime, it's pretty constant-like. And up here, it's also pretty constant-like, so we can do the same game. We can tell Excel to lay down an equation of best fit, determine the slope of the line. The slope of the line here is alpha. In the small curvature regime, the value of alpha we get is about 0.030. This is what we found when we determined this guy directly. But then in this large mass regime, in this large mass regime out here, the slope becomes smaller, just as I suspected we needed to have happen in order for our data to become good. In this regime, alpha comes out to about 0.006. It's about 1/5 as big as it was in the small mass regime. So now what? Now you can go back to your data. I now use this new value of alpha that we determined directly. I measure all of these guys. Here's my average R again. Here's my period. Here's the mass. I then use this value of alpha that we found directly. I plot my data points, and this is what we get. Quite linear. Each one of these different kinds of objects correspond to different central masses. Here's my period versus this guy here. You can see, look at the period in here, about 0.2 to 0.5. This ball is zipping around really quickly when it gets inside here. There's also, I should mention, deep in the throat. In the small curvature regime, it's circular-like. It actually loses a fair amount of the radius on each revolution. But deep in the well, that's not the case at all. It's also another thing we were fighting in the small curvature regime. It's pretty easy to get elliptical-like orbits. Down in the well, it goes almost as circular every time, so it's not hard at all in this regime. Anyway, the experimental value we find by the slope of this line gives us effectively 2.62. This is what the slope is theoretically. If I plug in G as 9.80, I get this value here, 2.37. So they're pretty close. How close? About 10% error. Get about 10% error when I use this value of alpha, which isn't, well, it may sound like it's off by a bit, but when I used the alpha from before, I find about 94% error, and it's not even close to being linear. This was effectively some of the main results of the paper, or of the work from the summer. I know I don't have a whole lot of time. I got about maybe 5 to 10 minutes. Let me quickly outline to you now. I want to run this analogy a little bit more. So again, we started this talk off by talking about the analogy that people think of then marbles rolling on fabrics of some sort to mimic effectively particle orbits around some objects. So let me carry the analogy out. This is called the line element. And I don't want to, this is all coming out of general relativity, but I'll try to get a basic idea. ds squared is a length in a 4-dimensional sense. My 4 dimensions here is my coordinate time t, and then spherical polar coordinates r, theta, and phi, right? And what this corresponds to, this is the length element for a spherically symmetric, non-rotating massive object, like we started with. But now what I'm going to do is look at allowing for a cosmological constant. Cosmological constant or a vacuum energy. The history of the cosmological constant and vacuum energy is actually quite interesting. It was first embraced by Einstein, then later abandoned, and now we rethink about the universe as having a vacuum energy itself. You think, now physically speaking, they're absolutely different things. You think of the cosmological constant as some curvature input effectively, and you think of the vacuum energy as coming from the energy of the vacuum itself, but mathematically speaking, they're the same thing. This rho is the vacuum energy, lambda corresponds to the cosmological constant. They're exactly the same thing except they're off by a constant, so I can think of either one. So here I have this is the exact solution for a spherically symmetric massive object, non-rotating, in a cosmological or vacuum energy background. G, again, is just the constant, Newton's constant. M is the central mass. R is my radial coordinate. Lambda is my cosmological constant. Lambda can be positive, negative, or 0. If it's 0, this just reduces to the Schwarzschild solution, right? That's what we started with. If lambda is positive, then this solution is called the Schwarzschild de Sitter space-time. This corresponds to, when positive lambda, this corresponds to, in fact, they actually think now that we live in a universe as a positive cosmological constant driving the accelerated expansion of the universe itself. Lambda can also be negative. If lambda is negative, this is called the Schwarzschild anti-de Sitter space-time. Now, this one seems to correspond or fit with what we actually observe. I'm going to actually be more interested in this work to this guy here. This guy gives rise, effectively, you can think of it as a repulsive type of a force due to the vacuum energy. This guy, you can think of it as an attractive type of a force due to the vacuum energy. Let me not bog you down with the details too much, but what you do is you start off with this solution, the geometry that I just talked about. You do something called normalizing the 4 velocity. The details aren't so important. This theory has a couple symmetries. One is a symmetry in time, and the other is a symmetry in my angular coordinate phi that gives rise to 2 conservation laws. I put these all together, and what I come up with is what's called the radial equation of motion. What this is, if you look closely, it looks like conservation of mechanical energy for a particle moving in 1 dimension. That's how you can think of it. E effectively is your total constant energy. Here is the time rate of change, your r coordinate with respect to, it turns out this is proper time. And this is what's called an effective potential energy. This is effectively equivalent to an equation of conservation of mechanical energy per unit mass, where here's my effective potential energy. Now, if you look at the effective potential energy, these 2 terms come out of Newtonian theory. Here's your 1 over r potential in Newtonian theory. Here's a 1 over r squared, which comes from the angular momentum of the guy that's actually moving around. General relativity actually gives rise to a correction term. If you have no lambda, no cosmological constant, just a Schwarzschild solution, general relativity gives rise to a 1 over r cubed correction term. This tells you that general relativity is going to predict deviations from Newtonian theory for a small r regime. Lastly, when I have my cosmological constant, here's this L is just corresponding to your angular momentum. Effectively, it's a constant. And then you can see this term grows with r. So the cosmological constant or vacuum energy gives rise to a large r correction. So what do we want to do? What I want to do is I want to take this expression, I want to explore circular-like orbits because I'm going for the analogy. I'm trying to probe the analogy here. So how do I find circular orbits? Well, if you've had advanced dynamics, again, you know you take the potential and you take the derivative with respect to r theta equals 0. That corresponds to the trough of the peak of some curve. That's where you get your circular orbits. The second thing you do is you set dr dt equal to 0. That says you have no radial motion at all. When you do this and you play around with the mathematics, you can come up with the Kepler expression. And here it is. This is an exact solution. This is the exact solution it's an exact Kepler-like expression for a constant spherical mass in the presence of a vacuum energy. If I set lambda equals 0, notice that this reduces to Kepler's third law. It's kind of remarkable that in general relativity, Kepler's third law is exactly the same as it is in Newtonian gravity. It's true, but it is. And here I have, if I allow for a cosmological constant term, what do you see? Well, here I have two competing terms in the denominator, right? I have the central mass, and then I have this vacuum energy density. Now, let me remind you, you probably forgot, it's been so long now, this is the Kepler-like expression for my marble rolling on a warped spandex fabric in a small curvature regime. Again, notice the 2 and the 3 have been switched, right? Here's my term from the vacuum energy density. Now, this is pretty interesting. Look at what is this lambda? If I want to write this in terms of the vacuum energy density, lambda is 8 pi g times rho. C is equal to 1 here. If I plug that in, this becomes 8/3 pi r cubed times lambda. That's 4/3 pi r cubed is the volume of a sphere, of course. So this is energy per volume times 2. And this is effectively, well, here's my mass, here's my mass per area times area. So what's kind of fascinating is, although I started the talk off by showing that you cannot have surface whatsoever that will give rise to motions that will mimic planetary motion. You can't, because it's different no matter what. For a spandex fabric, this areal mass density effectively plays the role, if I push this analogy far enough, this areal mass density plays the role of a negative cosmological constant, which I thought was kind of cool. Anyway, that's the appendix of this paper. So anyway, let me wrap stuff up with just telling you effectively the conclusions. Here's the main things that come out of the paper itself. Number 1, the mass of the spandex fabric interior to the orbit of the marble actually matters. In fact, it could dominate for a small enough central mass, which we showed and collected data on. Number 2, the modulus of elasticity describing a spandex fabric is not constant. It's in fact a function of the stretch, which tells you that my spandex fabric is not a truly elastic surface like I may think. And then lastly, if you push this analogy far enough, you could then think of the mass density of the spandex fabric as playing the role of the vacuum energy density of a space-time where I have a central mass and a vacuum energy density existing there. Anyway, with that being said, let me conclude. So thank you very much for coming. That's it. Dr. Sheik.
I couldn't follow all the equations, but you mentioned something about you were concerned about the pre-stretch. Where in the equations were you actually saying there's no pre-stretch?
You didn't see it. You probably, I don't know if I know you read Michael's talk last year. I don't know if you remember or not. We have these expressions, and you can actually look at when you write down the Lagrange, and you can allow for a pre-stretch. You have to let your R be the initial amount by some amount epsilon. If you remember correctly, what we had was we had two. I don't know if you remember at all. It's been a while. We had two terms, and what we did was we actually expanded for small pre-stretch for a given. I don't know if you remember this at all. It became an absolute mess. We tried to account for it, and it was quite hairy. I decided this summer we absolutely don't want to look at any pre-stretching whatsoever. You got to put it in effectively. You have to shift your R.
Okay, thanks.
You're welcome.
First, can you go back to the equation with the Z?
Which one? The original one? The initial disgusting equation?
Yeah, the one with the
Or beautiful equation, depending on your perspective, I guess.
Okay.
Well, let me bring it to the original one. The original one, I think I did zip by it, didn't I? There. This guy? So yeah, the second equation determines the shape. It's nonlinear. You cannot solve it analytically. What you need is Z prime. That's right. Well, yeah, okay, I got to be careful what I say. You could solve for Z prime by doing that, but then integrating it would be...
No, but you don't need Z. You don't need to integrate, do you?
Well, if you wanted the shape, you would. But no, you're right. Absolutely, you're right. Yeah.
So if you do solve for Z prime, then... Or did you try?
You just... No. At one time I actually entertained the idea. It's like a fourth order. It's hairy. Yeah. No, different student research project next year maybe or something. Anyone else? Yeah, Tom.
So, what do you think the implications of like the negative cosmological constant means?
In regards to this talk or in regards to the universe itself? So the way I kind of think of it is this, right? So again, I'm guilty as anyone of using this analogy of marbles rolling on a spandex fabric to talk about motions. And it turns out that that's not really precise. You can't do it because you can't mimic exactly But I still think that the analogy is nice, right? So when you think of then a negative cosmological constant or negative vacuum energy density, that's effectively giving rise to an additional attractive force. Like then the fabric warping down gives rise to an additional attractive force. So what I think is even more fascinating is what would then a positive cosmological constant mean, which is what our universe seems to have. The analogy I'm thinking of, I think in terms of spandex fabric, is the fabric actually rising up, but then being divoted off by then this central mass. So when you go for a large R regime, that central mass plays a very tiny role. This causes then this repulsive type of a force which drives the accelerated expansion. Now again, I got to be careful when I'm saying I'm using this analogy to loosely think of this in my mind. But yeah, in this talk, in this paper, it's just kind of fun to play around with it and connect the two. And I was thinking it's got to be connected somehow. It took me quite a while to figure out how to do that exactly, but it works out. So.